Let me finish off with one more really ingenious test of special relativity. And that's related to little tiny particles that are created in nature. They're called muons. Muons are a type of subatomic particle. We don't need to worry about their nature, but a couple of things about them that you need to know. One is that they're created high in the upper atmosphere of the Earth. Cosmic rays, high energy cosmic rays from space strike particles in the upper atmosphere and create these muons 10 kilometers above the ground. And these muons are moving at incredibly high speeds, at about 98% of the speed of light. So there's our muon being created. The second thing you need to know about muons is that they are incredibly unstable. They don't last very long before they break apart into other subatomic particles. They last for about 1/1,000,000th of a second when they're created in labs here on Earth, and they're stationary relative to us. They last about 1/1,000,000th of a second before disintegrating. So we can detect these muons. We can set up muon detectors, but we wouldn't expect to find many because those muons only have 1/1,000,000th of a second to make it 10 kilometers down to the surface of the Earth. And even at 98% of the speed of light, almost all of them will have disintegrated long before they make it to the ground. We can do the calculations. And in 1/1,000,000th of a second, for every 3 million muons created in the upper atmosphere, only a single one should make it to the ground. So we should detect 1 muon out of every 3 million on the ground. The really bizarre thing is we detect about 150,000 out of every 3 million. So our prediction is off by 150,000 times. We see 150,000 more muons than we should based on their distance, their speed, and how long they last. We can't deny this empirical observation. Can special relativity provide us an explanation? Well, yes, it can, because remember that if these muons are traveling at relativistic speeds at 98% of the speed of light, then we need to account for the relativistic effects of length contraction and time dilation. So imagine that you are looking at one of these muons that is moving relative to you from the ground. Well, remember the muons look like they're approaching you at 98% of the speed of light. They are approaching you at 98% of the speed of light. What effect will that have on the time of that as you observe it for that muon? Well, remember time dilation. The time of the muon will be stretched out, so its time will slow down. And in fact, at 98% of the speed of light, the time is stretched out to 7 times its length. So 1/1,000,000th of a second for a stationary muon stretches out to 7/1,000,000ths of a second, 7 times as long for a muon moving at 98% of the speed of light. And that, if you do the calculations, gives enough time for about 150,000, the observed 150,000 out of every 3 million muons, to reach the ground. So in this case, our explanation is that they're lasting longer. But remember that what Einstein is really telling us is that what space and time look like to you actually depends on your relative motion. So consider this from the point of view of the muon. As far as the muon is concerned, it's sitting still and the ground is rushing towards it at 98% of the speed of light. Now, what's going to happen then to the length of the space between it and the ground? Length contraction says that that distance will actually shorten. So as far as the muon is concerned, what looks to us like 10 kilometers of atmosphere actually shortens to 1/7 of that. It shortens to 1.4 kilometers of atmosphere. And even surviving for only 1 millionth of a second, because for the muon, time doesn't change, but surviving 1 millionth of a second, 150,000 muons can travel the 1.4 kilometers to the ground before disintegrating. So which is it? Is the time, is it 7 millionths of a second that these muons survive, or is it that they're only traveling 1.4 kilometers instead of 10 kilometers? The answer is yes, it's both. Again, this is the mind-blowing idea behind special relativity, is that what the universe is like, everything you can observe about it depends on your relative motion. From the point of view of the ground, the muons are lasting 7 millionths of a second and crossing 10 kilometers of space. From the point of view of the muon, they are lasting 1 millionth of a second of time, but crossing only 1.4 kilometers of space. And both of them are equally true. Time, space, merge, blend, they're malleable, they depend on your position. The one thing that is, on your motion, the one thing that is constant for everybody is the speed of light.